All right, so we got the basics of solving a polynomial inequality in the last video. Here's another one that's got a few extra things to worry about, but we can apply, I think, some things that you'll probably have remembered from Algebra 1 and Algebra 2. So here is a quadratic inequality that I want to solve. I've changed the variable. This has a t instead of an x, but I think we'll be okay. Our number one first step is to try to move everything to one side so we have 0 on one side, so that we can start to think about this using a picture of a function, which would be parabolic, and then think about what the intercepts are. This is where in this case, the t-intercepts are for that associated function. That's where our function, this polynomial, is going to change from positive to negative. So I'll write this out. Again, you have no obligation to write this out. I'm going to add t squared to both sides and subtract 4 from both sides. I know I'm going to have to factor, so I'm just going to rewrite this polynomial in standard form. So this is going to be t squared plus 3t minus 4 is less than 0. So remember, this means I want to know what t values make this polynomial, this trinomial, negative. So the way to do that is to start by figuring out what t values make this polynomial exactly equal to 0. I'm going to do that by factoring. That's t, let's see, plus 4, and t minus 1 is less than 0. I'm going to come up here. I'm going to start my number line graph. Remember, we call this a sine graph. So I could imagine now that I've factored what t values make this polynomial equal to 0. Those are negative 4 and positive 1. So where t equals negative 4 and t equals positive 1 are the only places where this polynomial is going to be able to change from negative to positive or positive to negative. So I'm going to think about substituting in a t value from each one of those intervals. I know in the last video I took the intervals from right to left. I usually go from left to right, so let's see if we can do that. What if I let t equal negative 5? What if I arrange this slightly differently? I'm going to say, what if I let t equal negative 5? This way, I'm going to be able to keep this safe. I'm going to ask myself if letting t equals negative 5 gives me a true statement here or a false statement here. So I could go through and I can replace each one of these values. Feel free to do that. Here's what I actually do. I replace t with negative 5 in my head, and I say, well, negative 5 plus 4, that's a negative result. And negative 5 minus 1, that's another negative result. If I take two negative numbers and multiply them together, the result is positive. Why did I put the plus sign there on my number line? Because I had chosen a number that was less than negative 4. So I chose these two roots have divided my number line into 3 sections, and the t value I chose to check first is from the leftmost section of the number line. What if I let t equal, okay, I need something between negative 4 and 1. 0 is an easy choice. It's going to be 0 plus 4 is positive, and 0 minus 1 is negative 1, which is negative. So I'm going to be multiplying a positive number times a negative number. The result will be negative. But if I let t equal something to the right of 1, I could just choose 2. 2 plus 4 is 6, which is positive. 2 minus 1 is 1, which is also positive. I'd be multiplying two positive numbers together and get a positive result. Now that I've filled in my sign chart, I go back to the version of my inequality that has a 0 on one side, and I notice that I want to know what t values make that polynomial negative. Less than 0 means negative. So here's the one section of my number line where I got negative results. So my answer is going to be negative 4 to 1. That's parenthesis bracket notation. I can also write negative 4 is less than t, which is less than 1. They both get full credit. If there's anything about this that's going to make you think that was an ordered pair, then get in the habit of writing this. Okay, so wait a second. We just had two problems in a row where sort of the middle section was our answer. So it's not totally a coincidence. One of the patterns I want you to think about that the graph. If I were to graph t squared plus 3t minus 4. So y equals t squared plus 3t minus 4. Hey, that's a parabola. The leading coefficient is positive, so I know if I graph it, I'm going to have an open up parabola. By the process of factoring, I figured out what those two intercepts are. They're -4 to +1. If I'm able to interpret this statement here to mean what values of t make that parabola lie below the axis, well, an open up parabola, if you want to call it that, a parabola with a leading coefficient that's positive, is negative on its middle section, assuming it has two intercepts. So that's something to notice, that if we have a degree 2 inequality to solve, and we find two roots, two x-intercepts, or in this case t-intercepts, then our graph is going to behave like we want it to behave, and you can go ahead and use some shortcuts and make some assumptions. So we're going to see an example next where this is not the case. Okay, so here's an inequality I want to solve. 9x is less than or equal to x cubed. This is a cubic inequality. It's not quadratic anymore. You probably don't have as much experience graphing cubics, but cubics, well, you know y equals x cubed looks like that, approximately. Thank you for your open-mindedness. A cubic can actually change direction twice, so you'll find that most cubics look like this if they have a positive leading coefficient, or like this if they have a negative leading coefficient. You can imagine arrows on the ends there. Okay, but let's see if we can use this same technique. And the answer is yes, of course we can. So start with here, we're going to try to isolate the, well, we're just going to try to have a 0 on one side so that we'll be able to use the zero product property to factor, to find the roots, those x-intercepts. So I might say 0 is less than or equal to x cubed minus 9x. There's certainly more than one way to rearrange that. I'm going to factor this. X squared minus 9. Oh, this is interesting because this factors further now. So 0 is less than or equal to x times x minus 3 times x plus 3. If you really, really, really like to read things from left to right, which I totally get, you could say that this is the same as x times x minus 3 times x plus 3 is greater than or equal to 0. So we're going to be looking for any x's that make this polynomial positive. Greater than or equal to 0 means positive or equal to 0. We're going to do the same thing. We're going to start with a number line. We're going to mark all of the x-intercepts. So what values of x would make this polynomial equal to 0? Well, they are 0 and positive 3 and negative 3. Okay, so notice here we have a cubic inequality, and we did in fact find 3 roots. That's good. When that happens, let's see, what was the word you used? Multiplicity. So that means none of the roots, we found 3 separate distinct roots. The multiplicity of each root is 1. There's no repeated roots. Repeated roots, they take like a touch extra work, and they show up on the AP test every year. So, but you notice when you don't have any repeated roots, if you could figure out what one section of your number line is, positive or negative, then the other sections are going to alternate. So we can test them all out. So what might I try here? I might try x equals -4. If I let x equal -4, that's going to be a negative times a negative times another negative, and that result is going to be negative. If I let x equal something between -3 and 0, so how about like -1? That's going to be a negative times a positive. If I multiply two negative numbers by a positive number, the result is positive. I can keep checking here. If I let x equal +1, I'll write this out again. I have x times x minus 3 times x plus 3 is greater than or equal to 0. If I let x equal +1, it's going to be a positive times a positive. Oops, nope. 1 take away 3 would be negative. 1 plus 3 would be positive. So I'm going to multiply two positives by a negative. That's a negative result. If I let x equal something bigger than 3, I'm going to have a positive times a positive times a positive. Have a positive result. So I'm going to go back to what I had here. I want x values that make that statement, that polynomial, positive. Well, they're everything between -3 and 0 in union with everything from 3 to infinity. That's parenthesis bracket notation. If you want to use the x's in your answer, you could say -3 is less than x, which is less than 0, union 3 is less than x, which is less than infinity.